Anytime you see molarity, you want to be thinking big M for moles per liter. So you're going to see this in a lot of different types of problems. So in the first example, you're going to ask how you would create. So this is a written as well as a calculation problem. So in order to figure out how much I need to make, I need to know what I'm making, or how much I'm making, what concentration, and of course what the substance is that I'm making it from. So you want to always start with your measured unit, which is going to be this. So we're going to start a bridge problem with that value. So the thing that you need to think of is, for the final unit, is what are you making it from? Since this is an ionic compound, they are typically solids at room temperature, so I'm going to need grams of chromium chloride in my final answer. So AP does allow you to convert metric in your head, so if you can go that this is 250 milliliters is 0.25 liters and just start from there, that's okay. If you need the structure of the metric, that's okay too, as long as you get the right answer. It doesn't matter what steps you need to get there, but again, the moles per liter you need to think of in that ratio, and if you're doing it with just straight to liters, it would look like this. And then you're going to need the molar mass of the chromium chloride, which is 158.35 grams per mole. And again, either way will get you your answer here. And since I'm out of space here, I'm just going to write it down here. You get the same thing no matter which way you go, 19.8 grams. Now you're not done at this point because you need to explain how to make that. So once you would measure out the 19.8 grams, you would dissolve that in enough water to completely dissolve it, but not exactly 250 milliliters. You would have less than that. So if I were making this, I'd probably dissolve it in a 100 milliliter beaker quantitatively, rinse that, transfer all of that into a volumetric flask, and you'll see pictures of this in your textbook, and also then at that point dilute to the 250 milliliter mark. So you would have to write those steps out in order to complete this problem. In this case, you're starting with a known mass of a compound. So this is the systematic name for naming a hydrate. So you should recognize hepta as 7. So your formula is going to be FeSO4.7H2O. That's going to be important because you're going to need to factor this into the molar mass. So you'll do the molar mass of this and then add 7 times the 18.02 grams for water to get the total. And again, we need to know what volume of solution we're making. So this one is simply just a ratio. And since molarity is moles over liters, this is going to be like a density problem where we start with both parts. So I'm going to have 100 grams over 2 liters of solution. You'll see I don't need to do anything with the liters because it's already in liters, but I need to do the full molar mass, which is 278.05 grams in 1 mole. And that gives me my units of moles per liter, and when I do the math, I get 0.180 moles per liter, or you could label this as big M, either's fine, but you just, again, need to know that this is the units you need for that. Example number 3 is similar because you're given a mass, and this time we're giving you the formula. And the reason I wanted to show you this is sometimes you will see this written this way. So CH3 COO is C2H3O2. So you may not recognize acetate in this form, but that's its structural form. So they're equivalent. And again, we need to know the volume of solution. So I'm going to start with my mass over volume. And again, if you're comfortable and you want to do 75 over 0.5 liters, that's fine. If you need that step, that's fine too. And to cancel your grams, you need your molar mass. And that gives you 0.948 molar of the calcium acetate. Again, in either form you can write it. So that's the first part of the question. The calcium ions comes this idea of net ionic equations. When calcium acetate dissolves, it basically splits into calcium ions and two separate acetate ions. So those are released into solution individually. So the calcium you'll see is 1-to-1 with this, but again, you should show some kind of relationship for that, it's a 1-to-1 mole ratio with the calcium acetate. Again, I'm doing this instead of doing a bridge problem just to show that's an acceptable way to do it. So that would be also 0.948 moles per liter. For the acetate, we need to factor in the fact that there are 2 moles. So for every 1 mole of acetate, or excuse me, calcium acetate, there are 2 moles of the acetate, and I'm just going to abbreviate that AC since I'm running out of room, which would give you a concentration of 1.90 moles per liter. So you have to account for the fact that there's twice as much of that in the chemical formula. Okay, this last one makes use of the dilution equation, and you'll either see that as C1V1 equals C2V2, or sometimes M1V1 equals M2V2 if you're using strictly molarity. So as I read my problem, I just need to define my conditions. So this first number here I'm going to label as V1, and then this would be M1 or C1. And then the concentrated would be my M2. So in order to figure out how much to make, I just need to substitute those into my equation. So the 3.00 molarity times the 250 milliliters. And for this equation, it does not have to go to liters as long as your units match on the other side. So this would be 12.1 molar and V2. And when you do the algebra for that, you get that V2 is 62.4 milliliters. And you have to add that to a volume of water that's less than 250, and there's a safety rule that goes here that you always add acid into water, so you don't want to add water into concentrated acid. It's kind of like adding water to grease. It would spurt back out at you. So you would add the 62.4 milliliters to maybe like 100 milliliters of water, and then you would dilute it to your 250 milliliter mark, and then mix that up to get your diluted solution. So that concludes page 1 of the molarity or solution stoichiometry notes.